Hello students, in the last class we studied construction and propagation mechanism in an optical fiber. Now you are going to study angle of acceptance, numerical aperture, types of optical fibers and attenuation. See this diagram. Here N0 is refractive index of surrounding medium, N1 is refractive index of core and N2 is refractive index of cladding, which is shown here. Consider a ray of light AO which is made to incident on the point O, which is present on the axis. This is that fiber axis which is shown in dashed line. So this is that incident ray. Now that ray refracts along OB like this by making angle of refraction theta 1. This is a normal drawn here. This is another point of incidence at which light ray grazes the interface. It travels along BC. So we have to consider 2 points here. One point is O, another point is B. At the point O, theta naught is angle of incidence, theta 1 is angle of refraction. At the point B, 90 minus theta 1, it is not written here, this is that angle. 90 minus theta 1 is angle of incidence and 90 is angle of refraction. So at the point B, if angle of refraction is 90 degree, then angle of incidence is called as critical angle. So 90 minus theta 1 is taken as critical angle. Consider another ray of light which enters the core here. This is another ray of light and its angle of incidence is greater than theta naught. Now that ray refracts along OB and again refracts from B to the surrounding medium. So let us take one more case here. Take another ray of light which enters the core and its angle of incidence is less than theta naught. Now that ray again refracts along OB, but it does not refract, it undergoes total internal reflection. So we have to consider three cases here. First case, angle of incidence at O. If theta I, angle of incidence, is equal to theta naught, light ray grazes the boundary of core and cladding. If theta I is greater than theta naught, then light ray undergoes refraction. And if theta I is less than theta naught, light ray undergoes total internal reflection. So we want a third case here. So due to total internal reflection, light ray propagates through optical fiber and this is considered as a condition of propagation. So in three cases we have one angle that is theta naught. That angle is called as angle of acceptance. So angle of acceptance is the angle of incidence at which light ray propagates through optical fiber. It is given here. Next is numerical aperture. Numerical aperture is a sign of angle of acceptance. Sine theta naught. Sine theta naught is taken as numerical aperture and it represents light gathering capability of the optical fiber. If numerical aperture increases, then its light gathering capability also increases. So this is about angle of acceptance and numerical aperture. Now let us derive an expression for numerical aperture. See, same diagram is taken here. Now consider 2 points. One point is O, another point is B. At O, two angles we have to consider. Theta naught is angle of incidence, theta I1 is a angle of refraction. At B, angle of incidence is 90 minus theta 1, angle of refraction is 90 degree. If you apply Snell's law at O, we have to consider two refractive indices N0 and N1. N0 sin theta naught is equal to N1 sin theta 1. At B, N1 sin 90 minus theta 1 is equal to N2 sin 90. It is given here. N0 sin theta naught is equal to N1 sin theta 1. Second case, N1 sin 90 minus theta 1 is equal to N2 sin 90. Now let us consider the second case. Sin 90 minus theta 1 is cos theta 1. So N1 cos theta 1 is equal to N2. So that implies cos theta 1 is equal to N2 by N1. Now let us consider equation 3.15 again. First equation here. There we'll take sin theta naught on left hand side. Then that is equal to N1 by N0 sin theta 1. Sin theta naught is equal to N1 by N0 square root of 1 minus cos square theta 1. Since sin square theta 1 plus cos square theta 1 is equal to 1, therefore sin theta 1 is equal to root of 1 minus cos square theta 1. Let us substitute equation 3.17 in equation 3.18. We have to substitute for cos theta 1. So we get another equation here. Therefore sin theta naught is equal to N1 by N0 root of 1 minus N2 square by N1 square. So sin theta naught is numerical aperture, which is written as N dot A. That is equal to, in the square root here, take N1 square outside, it becomes N1. So we can cancel N1 in the numerator and denominator. We get equation 3.19. So which is equation for numerical aperture. Here N1 is refractive index of core, N2 is refractive index of cladding, and N0 is refractive index of surrounding medium. Suppose if surrounding medium is air, then N0 becomes equal to 1. So sin theta naught or numerical aperture becomes equal to simply root of N1 square minus N2 square. So this is also expression for numerical aperture if surrounding medium is air. Now we'll take the condition for propagation. Let us consider theta I as angle of incidence on the core. As we studied earlier, for this condition, that means that theta I should be less than theta naught. Only for that light ray undergoes total internal reflection. So apply sine on both sides. For this, we get sin theta I less than that of sin theta naught. So sin theta naught is numerical aperture, or we can say that condition for propagation in an optical fiber is numerical aperture should be greater than that of sine of angle of incidence. So same thing is written here in the form of equation for numerical aperture, which is taken as condition for propagation. So this is about the expression for numerical aperture and condition for propagation. Now one more case, fractional index change. It is given by delta is equal to N1 minus N2 divided by N1. It is defined as the ratio of difference between the refractive indices of the core and cladding to the refractive index of the core of an optical fiber. It is required for problems. If N1 and delta is given, you can calculate N2 and vice versa. Next concept is modes of propagation. Mode refers to number of paths for light rays. If light ray follows a single path, then it is called as single mode. If light ray follows multiple paths, then it is called as multimode. So mode in an optical fiber is determined by a parameter that is called as V number. So V number is given by V is equal to pi d by lambda into numerical aperture, that is equal to pi d by lambda into square root of n1 square minus n2 square divided by n0, where pi is a constant, its value is 3.14, d is core diameter, lambda is wavelength of light propagating in an optical fiber. So by using this V number formula, we can find out number of modes supported by the fiber. So it is given as n is equal to, this is equal to n, okay, and n is called as number of modes, that is equal to v square by 2. So this expression is required to calculate number of modes in an optical fiber. Now we will take types of optical fiber. There are three types. First one, step index single mode optical fiber. Second, step index multimode optical fiber. Third, graded index multimode optical fiber. The above three types are considered according to core diameter and refractive index profile. Let us see first one, step index single mode optical fiber. Three diagrams are shown here. First one is geometry, second one is a refractive index profile, third one ray propagation. So first, geometry indicates diameter of core and cladding. Inner circle indicates diameter of core and outer circle indicates diameter of cladding. For single mode optical fiber, diameter of core is 8 to 10 micrometer and diameter of cladding is 60 to 70 micrometer. That means this optical fiber has got narrow core. Second diagram is refractive index profile. So refractive index profile is a curve which represents variation of refractive index with respect to radial distance. So what are the characteristics of this single mode optical fiber? Already mentioned, it has got narrow core. N1 and N2. N1 is refractive index of core, N2 is refractive index of cladding. Both are uniform. They are not varying. But for any optical fiber, N1 is greater than that of N2. Refractive index profile takes the shape of a step. Because of these two factors, N1 is greater than that of N2 and both are uniform, we get a flat region in the refractive index profile. See, this is that region where N1 is constant and this is the region where N2 is a constant. This step indicates that N1 is greater than that of N2. Because of narrow core, it can guide only one mode. So only one ray is shown in ray propagation here. Only one ray is there. It needs laser as a source of light. And such optical fibers find application in submarine cable. So this is about a single mode optical fiber. Next we'll go for second one, step index multimode optical fiber. Here also geometry shows diameter of core and cladding. It has got large core diameter, that is 50 to 200 micrometer, and for cladding 100 to 250 micrometer. Because of large core diameter, it supports propagation of large number of modes. Then N1 and N2 both are uniform. N1 is greater than that of N2. So because of these two cases, we get a flat region in refractive index profile. N1 is uniform, N2 is also uniform, and N1 is greater than that of N2. So light ray follows a zigzag path here. In the previous case also, light ray follows a zigzag path. So laser or LED is used as a source of light. It is least expensive comparing to two other cases, and it finds application in data links. So that is about step index multimode optical fiber. Now I'll go for third one, graded index multimode optical fiber. It is also called as a green multimode fiber. Here in the geometry you can see the diameter of core and cladding. Both the diameters are same as that of previous one. Step index multimode optical fiber, no changes here. N1 is greater than that of N2. Large core diameter as mentioned earlier. Here only one main difference is comparing to second one. Refractive index of core is variable, but refractive index of cladding is uniform. So how refractive index of core varies? How N1 varies? Refractive index of core decreases in the radially outward direction from the axis and becomes equal to that of cladding at the interface. So here if you consider this as axis of the fiber, on the axis of the fiber N1 is a maximum, then on either side it decreases. And at the interface of core and cladding, N1 becomes equal to N2. This curved region indicates that N1 is variable and flat region indicates N2 is uniform. Here light follows curved path. Due to change in refractive index of core, light ray follows a curved path. It is most expensive of all, and it finds application in telephone trunks. So this is about graded index multimode optical fiber. Now we'll see our last case in this class, that is attenuation in an optical fiber. While light propagates through optical fiber, there exists a loss of power or loss of signal or loss of intensity. Such losses are called as attenuations. So it is defined as loss of power suffered by the optical signal as it propagates through the optical fiber. There are three mechanisms through which attenuation takes place. First one is called absorption loss, second one is scattering loss, and third one radiation loss. I'll say first one, that is absorption loss. Loss of signal power occurs due to the absorption of photons. Absorption of photon takes place in two cases. First one is called as extrinsic absorption loss. Second one is called as intrinsic absorption loss. So in extrinsic absorption loss, that name itself indicates that this absorption takes place due to the presence of impurities. Common impurities present in the fiber glass are transition metal ions such as chromium, iron, cobalt, and copper. Photons interact with these impurities and they get absorbed by the impurities. During this absorption, electron present in the lower state excited to higher state, and in the higher energy state these electrons are unstable. Soon they de-excite to lower energy state by emitting energy. Impurities give up their absorbed energy either in the form of heat or light. But emitted light has got direction and phase which is different from the incident photon. So this emitted photon is of no use. That's why it is considered as a loss, and that loss is called as a extrinsic absorption loss. Second one is intrinsic absorption. The fiber itself as a material has a tendency to absorb light energy, assuming material is free from impurities and inhomogeneities. Here, this absorption is very much less comparing to extrinsic absorption loss. Second one is scattering loss. Scattering of photons due to structural inhomogeneities in the optical fiber is called as scattering losses. Structural inhomogeneities induce sharp variation in the refractive index. Where there exists a sharp variation in refractive index, we have certain region. That region is called as scattering center. Any scattering center has got a dimension. So if dimension of scattering center is less than that of the wavelength of light, then that scattering center scatters the photon. That photon will come out of the optical fiber. Such scattering is called as Rayleigh scattering. So Rayleigh scattering plays important role in attenuation. So scattering center is shown here. See, this is that region where there exists a change in refractive index. If D is the dimension of this scattering center, and this dimension will be less than that of wavelength, then only there exists a Rayleigh scattering. So due to Rayleigh scattering, there exists a loss of photons. Third one is a radiation loss. Loss of signal due to bending of optical fiber is called as radiation loss. There are two types of bends, macroscopic bends and microscopic bends. Macroscopic bend is shown here and microscopic bend is shown here. In macroscopic bends, radius of bending is much larger comparing to the fiber diameter. So here the radius of bending exists and it is large comparing to fiber diameter. So such bends are called as macroscopic bends. While light is propagating through optical fiber, due to total internal reflection, it sustains in that. But due to bending, that light ray fails to undergo total internal reflection. It is shown here because angle of incidence will be less than that of critical angle. So light ray will refract out. So it is considered as a loss. That loss is called as radiation loss. Second one is microscopic bends. Microscopic bends are small scale repetitive fluctuations in the linearity of the fiber axis. You can see in the diagram here multiple fluctuations are there in which light ray fails to undergo total internal reflection because angle of incidence will be less than that of critical angle. So in radiation loss due to bending of optical fiber, light ray fails to undergo total internal reflection, so it is considered as a loss.